All right. My name is Nitesh Sehwani. I'm presenting this work, No Features Needed, using BP sequence embeddings for weblog anomaly detection. And so we are excited to be presenting at this venue, and let's get started. So a little bit about me. I'm an SD2 at the Managed Services team at AWS. I've been here for about 3.5 years now and really love it. Outside of work, my hobbies include photography, reading Agatha Christie thrillers, and also like security scoops online. And in the pic you see, it's me on the right with my sister on the left, and it was like 2 months back at the beach in the Maldives. It was really fun and sunny out there, and great memories. All right. So what is our premise for today? What's our premise for the work we have done? To put it straightforward in really crisp words, it's about designing an unsupervised technique for converting log data into vectors, which can be used in anomaly detection or, like we say, AD algorithms. Essentially, we want to have a technique for converting the log data, which you have from like any applications or any infrastructure components that you're running, to be converted into formats which can be ingested by AD algorithms, essentially ML algorithms used in AD. This is the basic idea of the paper, and we'll go into what our motivation was. So AMS, short form for AWS Managed Services, is a team inside Amazon, inside AWS, which deploys infrastructure across customer accounts. And we as a team usually have these concepts these days called innovation days once a month. And a couple of months back, during our innovation days, when we were brainstorming ideas, we realized it might be good to have a mechanism for monitoring our infrastructure across our accounts. So whenever, for example, we have software updates or like new application updates or even new applications going out, it might be good to have a mechanism to monitor their deployments. Now, industry-wide, there are like obviously various practices for monitoring deployments. Post you release them to new regions or new availability zones. Like, for example, you can run integration tests when you release your software updates to your service accounts. And then like if your integration tests fail, you roll back your code. What about, we thought, if we could automatically, once we do a software deployment, think about analyzing how the software behaves. And based on the analysis, if we see that the behavior is not as expected, roll it back. So this was just a brainstorming idea. So to get started with it, we looked at the first step. And the first step was the data. So how do we take the data that we have across our infrastructure and convert it into formats which we can use for anomaly detection? So we essentially set out some tenets which we thought like would be good requirements for our system for getting started with anomaly detection. So first and foremost, we wanted that any data conversion technique which we would apply to the data we have should not in any way contribute towards increasing the FPRs, false positive rates, across our accounts. So essentially, to just give a brief insight, whenever we have these alerts created, we internally create tickets corresponding to every alerts. And then we have operations teams who go on and look at the alerts and based on what the alerts are, they go and take the appropriate actions. So if we were to increase these false positive rates, we would end up having more operations time spent on alerts which are not even anomalous. And that would waste money for us, and it would cause resource waste, time waste, which we didn't want. So that was the first tenet which we had in our mind. Moving on, we didn't want to make any dataset specific assumptions. Now, what do we mean by this? When we deploy applications, we can deploy multiple applications. We don't just deploy one application. For example, if you're deploying something based on a container, there'll be different logs as opposed to something if you're, let's say, deploying on a Windows server. So there are going to be different logs based on the infrastructure or even the application which we'll deploy. So if you were to make any dataset specific assumptions, it would not be optimal for our processes because, and this ties on to the next point, which says requiring no manual application log analysis. Because let's say if you were to deploy an application one today, and then we wanted to analyze the data. So we would have cloud architects, we would have operations engineers looking into the data for the application we deployed, looking at the data, extracting features, and then testing out these features to be input into anomaly detection algorithms for training for us to automatically analyze in the future if we were to have an anomaly or not. Now, if we were to go on doing this for every new infrastructure plus application combination which we would have, we could run into resourcing issues wherein most of our time would be spent on analyzing the data which we have, which was really a no-go if we were to go in this direction. So these are some of the requirements we set before beginning our investigation. So once we had these tenets, we went into a literature deep dive to look at the existing techniques and if we could utilize them as they are, or like if we had to go on a different direction. So some of the shortcomings we indeed found was firstly with manual feature analysis, wherein you have cloud architects or operations engineers sitting, or like even experts, security engineers sitting out and analyzing data, coming up with features which can be input into your AD algorithms. So this was definitely not viable for at the rate at which we would do deployments across our environments. So that was what we didn't want to go with. Secondly, there are techniques which exist which use architectures, for example, Auto-Encoders or CNNs for converting your data into vectors, which can then be used into the AD algorithms. Now, this adds a training layer. If you were to consider a CI/CD pipeline, we would need to have a new training layer wherein we would have to first convert the data which we get into formats, which would then be used to like input to AD algorithms for even like training. So we wanted to avoid using as many additional training layers or as much training as we could possibly avoid. We wanted to avoid it. So that was another shortcoming which we found in existing techniques. Also, like it's not obviously evident that many of those techniques are also very highly precise, as in they might have higher accuracies, but they might also like fall back on the number of false positives they generate. And as already mentioned, at AMS, we didn't want to have these false positive alerts because it's real manual efforts which we would have to spend on and which would become costly to us. Now, with these shortcomings in mind, we also wanted some future goals to be accomplished by any technique which we were to investigate. And as we know, AutoML is becoming ubiquitous across the industry for analyzing the data which you have across a different set of algorithms and hyperparameters. So if down the line, if we were to go and choose AutoML for analyzing the data we have across all the environments, and which would obviously make sense if we could aggregate that analysis automatically, we wanted a technique which would not impart any of its underlying bias, like if it was fine-tuned to any data or any such specific analysis to be imparted to the AutoML techniques. What this would do is that we would get a result, an outcome, which would be influenced by the way we are converting our data into appropriate formats for ingestion into AD algorithms. So we wanted to keep as less influence on our AutoML techniques in the future as possible as like we could achieve. And also we wanted, this is the end goal of any system, which is to discover as many zero-day attacks as possible. So we not just wanted to detect known anomalies, which we know today are anomalous events, but also zero-day attacks, unknown anomalies, as we would call it, by our system. And so with these shortcomings with existing works and long shots expected from our future work, we set out to build a direction in which we could go on. Now, the direction, what was the direction? So when we analyzed when we went into the literature, we found that byte pair encodings. Now, what are byte pair encodings? They're basically a technique for tokenizing your data, essentially taking your actual data and converting it into tokens based on an appropriate algorithm, which can then be further processed. Now, byte pair encodings essentially take your data, find the most frequently occurring components, tokens, as you can say, subword components in your data, and extract them. So this has widely been used across NMT literature and has been known to deliver good outcomes. And so that seemed like a good start for us. Moving on, what happens after data tokenization? You need to convert it into appropriate vectors. Now, our tenet, as you can recall, was having no additional training. So if we were to have training to convert these tokens into vectors, that would defeat our purpose. So we started looking at pre-trained models, like publicly available models, which we could use into our system. Now, there are two major categories of pre-trained models which are available. They are word embedding models and sequence embedding models. So we further wanted to narrow down on the type of embedding model which you would choose for our system. And so when we went deeper into literature, we realized context could be useful in vectorization. And if we were to use sequence embedding models, which take the context of the entire log sequence into consideration when creating these vectors, that could definitely help us in achieving our goal. So with these two tenets in mind, we found existing sequence embedding models and went for the universal sequence encoder. Now, this is a publicly available pre-trained model, and it also uses transfer learning, wherein it is trained on generic data and can be used in multiple different domains. This was attractive because it also ties back to another goal which we had, which was to not make any application data specific assumptions. So with these directions in mind, we went on to design our system. So this is essentially how our system looks like. It's a very simple architecture. Essentially, when you take in the log data, you run your BP algorithm over it, which extracts the most frequent tokens from your log data. And once you have these tokens, you encode your sequences using those tokens. So you have your sentence log sequence converted into a sequence of the tokens which are extracted by BP algorithm. Once you get those tokens, you just pass them on to a pre-trained encoder, which is publicly available, which converts them into 512 dimensional sequence vectors. This is the output dimensional size and form for use, universal sequence encoder. Once you have those embeddings, you can directly pass them to anomaly detection algorithms, or you can do some post-processing. You can choose to do some of it, which we did in our case, which was as simple as taking the dimensional vectors, converting them into 1D NumPy arrays before passing them on to our AD algorithms. And this is it. This is the architecture which we chose to move forward with. So when we have the algorithm and the system ready, we need to see what data can we use for evaluation. So we used two publicly available data sets, which are HTTP SIG 2010 and ISCX IDS 2012. Now, these are testing and training sequences which we have, which we were using in our analysis. We also took a 3-day internal production MH, which stands for management host data. Now, this analysis was done after we submitted our research, so it's not a part of the research. Essentially, we took an internal infrastructure component and obtained its logs for 3 days which was about 45,000 instance log sequence instances. And these are mostly access-related logs. And we had 6,000 testing sequences. So we analyzed all these three data sets for our proposed approach. Now, the algorithms we used are the most widely used algorithms when we want to work with data where we have all normal training instances. So we used one class SVMs and isolation forests, and these were the parameter ranges which we went with. Of course, in the future, if we were to go down the AutoML route, we would have these parameters tested automatically for us. So we took the data, we took our system, and we ran the data through our system to get our outcomes. Now, this table is present in the paper, and we have it up on Amazon Science where you all can review it. Essentially, what we found was our technique, which we compared with other techniques. Now, what were the other techniques? We compared with manual features, which were fine-tuned for those data sets. We compared our technique with auto-encoders based techniques, which essentially use bigrams for converting them into vectors. We tested with fasttext, which is a word embedding algorithm on the data we have. We also tested with another approach, which is similar to us, except that in vectorization, after using BPE tokens, it uses the TF-IDF algorithm followed by simple separation based on punctuation and then auto-encoders. So these were the 5 techniques we tested, 1 of ours and 4 of the others. And we found that our technique had as good performance as the manual features in terms of accuracies and FPRs, while also outperforming the other automated techniques in terms of these parameters. It was observed across both the data sets, and yep, so that was the results we had across both the data sets for both the algorithms, which validated our approach on the data sets used. Now, this is the result on the internal data we had. And you can see we obtained similar results as we obtained on the public data set. Now, importantly, the public data set which we used were primarily HTTP application logs, while the one which we have used here for Intel production management host data were Windows application logs. Still web servers, but different architectures. So we observed good results across both of them, which essentially validates and it achieves our tenet, which was to not make any application or dataset specific assumptions when going on with our data set, when going on with our data representation technique. We also obtained some interesting insights when we looked at our results further. So what were those insights? Essentially, as we already saw, compared to fasttext, our BPE-based sequence embeddings outperformed as compared to word-based embeddings. They also had the least outcome variation, and this can be verified from the table when switching between ML algorithms. Essentially, the accuracies and FPRs don't vary as much as compared to the other algorithms on the other data sets. So this is a useful insight because this makes it suitable for AutoML purposes in the future, wherein you know that the data representation technique will not impart its influence on the outcomes, and rather it will be the data and the algorithm combination rather than the representation technique, which will give us the appropriate hyperparameter values. We also found out that our representation technique works better on shorter length sequences as compared to longer length sequences, log sequences. Essentially, we have more FPRs when we go with higher length sequences. Now, why is this important? A study which we have cited in our work shows that most of the requests on the web tend to be shorter length sequences, less than 150 characters, which are made across the web. So it validates that our approach can be used for all of these log data, which have these requests, which are usually shorter than 150 characters. Still, we found that our technique outperforms all the other techniques at all sequence length. Like, it's not just outperforming at shorter sequence lengths, it also outperforms at longer sequence lengths as compared to other techniques. These validated our choice of the representation technique system which we had, but it's always not just the outcomes. We also need to look at the resource usages which we had with our system. And so we found that our system, our technique, essentially, when you train these ML algorithms, AD algorithms, on the representations from our technique, while also extracting the representations, essentially the entire end-to-end process using our technique as compared to others, it takes up to 3.5 times more compared to when using manual features. Now, this is the end-to-end execution time into using our technique is the only time which is required for our system. Now, compared with manual features, we have not included the time which is taken by cloud architects or operations engineers or even experts in actually analyzing the data, extracting the features, testing them out before actually creating this final set of features, which can be input into the algorithm. So that entire time frame, that entire process is taken out when calculating this execution time, which really is fine by us because we are taking out the manual component and it's just the execution time, which is 3.5 times more, which if you see in whole, it's actually lesser than the entire process when using manual features. So it's worth the investment when that is taken into account. Now, compared with other automated techniques which we had, except auto-encoders, our technique completed quicker than them. And these statistics are presented in the paper, which can be referred to. That was for execution time. When we come to memory, we see that our technique is always more memory intensive than when using manual features. And this is also expected because manual features for both the data sets had no more than 15 features, as in 15 columns, but our embeddings essentially had 512 dimensions. So it is a given that the memory consumption would be higher as compared to when using manual features. It's also usually on the higher end of memory consumption when compared to other automated techniques, less than 1.7 times, essentially not more than 2 times greater. So this gave us some extra learnings, which we can use for future work. Essentially, we envision that reducing the dimensions of the embeddings which we obtain, if we reduce those dimensions, we can drastically reduce the memory consumption of our technique. And so there are some widely used dimensional reduction techniques available, such as PC and LDA, which can directly be applied to these embeddings. And we want to see how the application of these techniques to our embeddings would really work out, like whether if the reduced dimensions are really giving us the good outcomes which we currently have. Essentially, we want to reduce the dimension, the embedding dimensions, while also maintaining enough discriminativeness of the embeddings so that we don't lose the good outcomes we have right now. There are, apart from PC and LDA, there are specifically dimensionality reduction techniques as well, which have been proposed for embeddings. And we would also like to explore those if they can also help us reducing the dimensions, apart from PC and LDA, if they work for reducing our memory consumption. So that is the future direction. I already started taking steps in that direction. But yeah, that's the topic for our future work. And that brings us to the end of our presentation. We would like to thank the external services security team members, Baris Koskar and Ali Turkamani, for their early feedback, as well as AMS software development managers, Jack Ellis and Tyler Carlton, and also the AMS technical program managers group for their contributions in this work. that's it. Thank you all for giving us the opportunity for presenting. You all can contact me for any questions after we finish our current session at sehwani@amazon.com. That will be all for the presentation. Any questions?
All right, so we have time for a few questions.
Do you have a sample of the data that you could look at?
Yeah, HTTP, CSIC, and ISCS, IDX are actually publicly available data sets. I don't have it right now on my laptop, but these are like publicly available data sets.
Okay.
So you can access them over the net.
Yeah, another thing I was curious about is these data sets are released in like 2010 and 2011. So they're quite old data sets now. I wonder if you have access to any more recent data set or which is public or maybe private.
When we went for this evaluation, we chose these datasets specifically because we had their manual features available to which we could compare our algorithms with. With the more recent datasets which we have, we didn't find as such any good works where you could find good manual features which were evaluated specifically for those datasets. But the other data set which we have used, it was a 2021 data set, like the internal one, but that's not publicly available.
Okay, all right.
Yep.
Thank you.
Definitely.
All right, so do we have any questions from the people in the call?